Okay, in this video, I want to talk about surjectivity. Okay, so L is a linear transformation from Rn to Rm. Okay, so the initial definition of surjectivity, actually, let me write it like this. L is surjective if and only if, so these are going to be like defining characteristics. I'm going to list a bunch of defining characteristics of surjectivity. The main one, the first one that we saw, is L is surjective if and only if LV equals W has at least one solution for every W in Rm. Okay, so LV equals W has at least one solution for every W in Rn. Okay, that's one way to say this. Another way to say this is if ML, this is going to be the matrix representation for L. If this has this form here, the columns are V1 through Vn, then L is surjective if and only if the columns, or let me say it this way, if and only if the equation MV equals W has at least one solution for every W in Rm. An equivalent way of saying this would be the columns of M, really M sub L, are a spanning set for Rm. Okay, another way of saying this would be to say that M sub L has no row of zeros when in row echelon form. Okay, because if it has a row of zeros, that means the vectors are not a spanning set. So how can we bring in something else? So what about systems of equations? So the system, so again, if we have a system of equations, MV equals W, this has a solution for every W in Rm, if and only if the linear transformation defined by LV equals M times V is surjective. Okay, and so again, similar to what we looked at with injectivity, these are just some ways that the different concepts of surjectivity, spanning sets, and existence of solutions go together and relate to each other. So basically the point that I'm trying to prove with this video and the injectivity video is just to illustrate the fact that these concepts kind of go together. That surjectivity goes with spanning sets, goes with existence of solutions to linear equations. That's the concept that I'm trying to illustrate here. Okay, let's finally answer a similar question. Let's say L is a linear transformation from Rn to Rm. That is surjective. Sorry, that was supposed to be an M. That is surjective. Then what do we know? Do we know that M is less than or equal to N? Do we know that M is equal to N? Or do we know that N is less than or equal to M? Which one of these do we know? Well, again, if M sub L is the linear or the matrix for this linear transformation, okay, then what do we know? Okay, so it's surjective. So the first thing we know is that the columns of M, or M sub L, are a spanning set for Rn or Rm. Okay, so what does this mean? No row of zeros. Okay, so what does this mean? Every row has a pivot. Okay, so the number of rows. So the number of rows is always greater than or equal to the number of pivots. Okay, that's always true. The number of rows is always greater than or equal to the number of pivots. But since there's no row of zeros, this means the number of rows is equal to the number of pivots. Okay, and notice that the number of pivots, is similar to, we talked about this in the last video, the number of pivots is always less than or equal to the number of columns. Okay, the number of pivots is always less than or equal to the number of columns. This is true only when the matrix is in row echelon form. Okay, so the number of rows, that is equal to M, and the number of columns, that is equal to N. So overall, this says that M is less than or equal to N. Okay, so if L is a linear transformation going from Rn to Rm and it's surjective, then it has to be going from a bigger dimensional space into a smaller dimensional space. Or a more accurate or a more correct thing would be to say that if L is a linear transformation going from a smaller dimensional space into a bigger dimensional space, it cannot be surjective. Okay, that's a better way to say it. Okay, it's kind of the opposite of injectivity. And you need to think about why those two are opposites and why intuitively this makes sense. Okay, that's all I have. In the next video, we're going to look at some linear transformations and determine whether or not they are injective, surjective, bijective, that sort of thing.